Lecture 2 of motion in a circle. Let's do a recap on what we have done in the last lecture. We talked about motion in a circle. We consider the kinematics of the motion. The kinematic of circular motion is about angular displacement, it's about angular velocity as well as the tangential velocity. Okay, we have defined all these terms. Today what we are looking at will be the acceleration. For object moving at constant speed v, as shown in the diagram, okay, the radius of the circular path is r. At the position A, the linear velocity is va. This object is moving at constant speed. Sometime later, the object will be moving to the position B. The speed is still the same, which is v, but the final velocity Vb now will be as shown in the direction Bd. So my question is the object accelerating? To answer this question, you need to recall that acceleration is defined as the rate of change of velocity. So with that definition, the answer to the question is yes, the object is accelerating, because as you can see in position A, the direction of velocity is this way, which is different from that when the particle is at the position B. So although the magnitude of the velocity, they are the same, but the direction changes, so the velocity changes, and that's why there's an acceleration. So next we are going to derive an expression for acceleration. Because this acceleration is referring to object moving in a circular motion, so we give it a special name. Instead of just calling it acceleration, we call it the centripetal acceleration. So the centripetal acceleration A will be equals to the rate of change of velocity over time. Okay, so this is the same definition that we have for acceleration, rate of change of velocity over time. So to find the change in velocity, I will need to take the velocity at position B minus the velocity at position A. And how do I do that? I can't just sub in the magnitude because the directions are different. So I need to use a vector diagram. So I'm going to extend the vector, okay, at the position V. B, this is the direction of the velocity VB, extend it up. Okay, what is this angle that is between the two velocity vectors? Can you see that it's theta? How do I get this angle theta? Well, if you look at this angle, which is opposite to this angle theta, you should be able to tell that this is 180 minus theta. Reason being supplementary angle. So if this angle is 180 minus theta, and this is a straight line, the angle between the two vectors must be theta. So to get the delta V, I will have to take the velocity VB minus VA. So I need to change the direction for VA to minus VA. Okay, so this is what I'm going to do. Move out the vector VB. Okay, change the direction for that of VA. So with that, I obtain the vector diagram for VB minus VA. Then the resultant, which is the change in velocity here, will be given by this arrow here. Okay, this acceleration that we obtain is the instantaneous acceleration. So the angle here is actually small. That means the two positions have to be quite close, but I have drawn the diagram bigger so that we can see clearer, okay, all the different factors like VA, BB, as well as the angular displacement theta. So by right it should be small, and if you draw a small diagram, you'll see that the change in the velocity, right? Okay, if I shift this whole triangle up, this change in velocity somewhere in the middle will be directed towards the center of the circle. So the direction of the acceleration is the same as that of the direction for the change in velocity, because we say A equals to delta v over t. So whatever the direction for your delta v will be the same direction as your acceleration. So the direction of acceleration is towards the center of the circle, since the delta v is towards the center of the circle. Okay, next we are going to derive an expression for the change in velocity. Let's consider the sector, which is part of a circle. We know that the arc length S will be equal to r theta. If the angle is very small, the arc length will be approximately a straight line. So for small angle, the arc length is almost a straight line, and the arc length equals to r theta. So making use of this, I'm going to refer to the vector diagram that we have, whereby we have the two velocity VA, VB, as well as the change in velocity. So if you compare the two triangles, I can find my delta V by using V times theta, just like R times theta. So here will be V times theta. Okay, V is the magnitude of the particle's velocity, which is constant. So bring that in, delta V is V theta, so your A will be V theta over delta T. And we defined previously that theta, the angular displacement over the time taken, that is your omega. So from here we get A equals to V omega. And recall V equals to R omega, so A can also be expressed in terms of R omega squared, or we also know that V equals R omega, so we can express your A in terms of V squared over R. So there are three formulas for acceleration that you need to know. I'd like to refer you back to the kinematics tutorial that you have done. If you take a look at 1A part 1, can an object have a varying velocity if its speed is constant? Well, in context to circular motion, yes, because for object moving in uniform circular motion, the speed is constant, but the direction is changing, so the velocity is changing. So an example that you can give in A part 1 will be uniform circular motion. Okay, let's take a look at D part 1. Must the velocity and the acceleration of an object have the same direction? Well, in the context of uniform circular motion, answer here is no, not necessary. For the case of uniform circular motion, we derive that the direction of acceleration is always directed towards the center of the circle, but the linear velocity v is always tangential, okay, to the circle, so they are perpendicular.